So we will talk about what is digital or bang phase detector. Now the phase detectors that we have seen so far give you an output which is proportional to the phase. The DC output is proportional to the phase. Now in a digital phase detector we don't do that. We just want to see if the phase is early or late. That is, if it is leading or lagging. That's all. Okay. Now, of course, you can, when it's digital, you can have multi-level digital. Here we are talking about, in particular, a binary phase detector. So let's say the data is like this. Then again, we want to know if it is perfectly aligned, the clock is like this, okay. That is, the rising edge is in the middle of the data symbol period, and the falling edge is coincident with the transition. It's assumed that the clock has 50% duty cycle, okay. This is when it is aligned, and we will talk about clock with respect to data. So if the clock is too early, that means so you can see this is earlier than this, and this is earlier than this, and so on. Okay. So we are talking about this the falling edges, the alignment of the falling edges with respect to the data transitions. So when I say early, the clock is early, too early compared to the ideal clock that we need. And if it is too late, we can draw waveforms corresponding to that. Okay. We have it here. Okay. So what we want is an output, roughly speaking, it's 1 if it's aligned and 0 if it is late. 1 if it is early and 0 if it's late, or something of the sort. Okay. We need to know if it is this or this. How would we go about doing this? How would you come up with an arrangement that will tell you if the clock is too early or too late? So, you mean you use a linear detector and you get this, okay, then what do you do? Are you coming up with a scheme where you use a linear detector and quantize its output? Yeah. Okay. But I don't care, right? I just want to know if it's early or late. I don't really care about how early it is or how late it is. That's what a linear phase detector does, right? So characteristics of a linear phase detector look like this. So let's say this is the ideal point, whatever it is. In case of a Hawk phase detector, that is the rising edge is in the middle, whatever this is pi naught. So this is clock is, this is late and this is early. Normally we plot the characteristics of data minus clock phase, right? So if the clock is too early, then the phase is negative. If the clock is too late, the phase is positive. Now, this is the characteristics, these are the characteristics of a linear detector. What I want is, corresponding digital output, something like this. I just want to know if it is early or late. I don't care about how much. Okay.
And if you get the output as 0, then it is a NPTEL. Data will be a clock.
Okay.
The clock will be data.
Okay.
So if we are getting a 0 at the output, the clock is arriving at 0.
If we get a 0, so you are saying you look at the value of the clock at the transition of the data. Actually, that's a nice idea. I have not seen it before, but yeah, you can do that. Now, one disadvantage I see here is you use only one of the, like half the transitions of data, right? Because let's say this is rising edge, then you use only this and this, you can't use this one. Okay.
You can also put a negative in the block,
Yeah, so you can do that also. And what happens if data is aligned with the clock? So does the scheme work? Does everyone agree about the scheme? Does it give you digital phase detection? Yeah, when it's aligned, you will, let's say you have noise and maybe half the time you get 1 and half the time you get 0. So on average it is 0. That's okay, right? So that is like asking what is sign of 0, right? So in real realization, because of noise, it will give you, if it's random noise, then it will give you 1 half the time and 0 half the time, and on average it is 0. Okay. So first of all, are we in basic agreement on the scheme? Agreement on the basic scheme. Does it work, or do you see any problems? What? Does it work? So is clocking the clock with the data. So at the data transitions, you find out whether clock is negative or positive. So you know whether the falling edge of the clock is before or after the data transition. Okay. So clearly, if you get a 0, get a low logic level at the edge of the data, that means the falling edge happened before the data transition. If you get a high level, then the falling edge happens after the data transition. Okay. No, see, jitter is just phase. That only means that the phase of the data or phase of the clock is not uniform. Now, if you give jittery data to a phase detector, it is supposed to measure the jitter also, right? So, jitter is part of the phase. Maybe all you are saying is, okay, the clock is maybe not some fixed phase, but also you have some phi of t. But a good phase detector is also supposed to measure this, respond to this. Okay, so that's not a problem. Maybe that phase jitter is a problem for something else, in which case you have to clean up your system to get rid of that. Does it work or not? It works, right? Okay. So besides the fact that now it works only for half the transitions, and like he suggested, you can use another one with data bar and or a falling edge flip flop and get the other remaining stuff, and you can OR them or something other sort. You can combine them in some way. Okay. What is the disadvantage you see if you want to use this use this? Data has to be some full amplitude digital type of stuff, but not necessarily full amplitude. It has to have some amplitude that you need for the clock. Normally a flip flop needs a good clock, and the sensitivity from data to the output is very high, not necessarily from the clock to the output, right? Because If you, I mean, this is a slight practical problem, but yeah. So if you remember the circuit, generally you want the clock to be strong enough to flip the circuit from one side to the other. Okay. So if the data is of low amplitude or corrupted too much by ASI, then you may have a bit of a problem. Okay. So besides that, what else do you see? Why do we want this phase detector? Where do we want to use this? Where did you use the Hog phase detector? In a clock and data recovery circuit. So can you use this in the same way? So the other sort of disadvantages, yeah, this is a phase detector and I think it works with, except that there is the slight practical problem. You understand this, right? The clock amplitude has to be good enough to switch from one side to the other, from the sampling side to the latching side. Now if you apply data here, that may not always be the case. Okay. So, but even besides that, you would like to have clock and data recovery circuit. That is a single circuit that helps you find out the phase between clock and data, but also gives you the retime data once the clock is aligned. So that it does not do. Okay. So it just gives you the phase difference, but to sample the data, what you need to do is you have to put this in a phase lock loop. Okay. Somehow you complete the PLL around it, and then you take another flip flop with the clock applied to clock and data to D and get the data out. Now, whenever you use different components like this, you end up with some mismatch errors, etc., etc. So, you would like to, the phase detector that you use, that itself, if it gives you the data, it will be better. Okay. But yeah, this phase detection works. So, how would you do that? Just like the Hog detector, it had a number of flip-flops and you take the output from some of them, you get the retime data. Okay. So, can you come up with an arrangement where similarly you have the clock going to clock, which is clocking some flip-flop, and data going to the data of the flip-flop, but somehow it also gives you a measure of the phase difference. Let's say you are allowed to sample the data at the clock edges. Okay, that's effectively what I'm saying by saying that the clock has to go to the clock input of the flip-flops. So you are allowed to sample the data at the clock edges. Then how would you tell whether the clock is too early or too late?
We sample it, so we get a phase shifted form of the data.
Okay.
Then we compare the data at the
So that gives you something proportional to the phase difference.
at the edges.
So you have the data and you retime the data to the clock, then what do you do?
Compare the value of one of the actual version with respect to shifted version at the shifted version's clock transistor.
Okay, so you are saying, so this, you compare the values here. Okay, what does it tell you? First of all, at the shifted versions transition, you don't know the value of this, but you have to do it slightly earlier or later. Okay. No, okay, let's go through the scheme again. How many flip-flops do you have? 2. Okay. Okay. Second. Oh, okay. Okay. Why do you say that? So that was essentially what he was saying also, right? Essentially you retime the data. This is the original data, and data aligned to the clock edge, maybe something like this. And the second flip-flop takes this as the clock, and this is the data. Okay, so you get this. What do you do with this? Why? I mean, the data could have been like this, right? I mean, you're depending on the fact that this is a rising edge, is it? Is that what you're saying? Because this is your clock width with the rising edge, you will get one here. Yeah, so maybe the delays in the system will make it a little. The only issue is some clock to Q delay here. So there is Q is not aligned with the clock very well. Okay. So that will also work. So some of these things I have not seen myself. So maybe you can investigate it and see how well it works, etc. Okay.
Second output of the clock is the down pulse.
Okay.
That will always give like 0.5 or
Yeah.
0. That is like.
No, that will always give you half period, right? You are talking about the second XOR output in the Hawk phase detector. Yeah, that always gives you the half period. Then let's say we have data like this. Something of this sort, right? You are allowed to sample this with the clock, and you can use rising edge, falling edge, anything you want. So, how many points would you need to tell whether it is early or late? 2? 3? Why 3? Why not 2? 3. So, if you have a number of samples, first of all, can you do it with sampling once per symbol period? Sampling only once in every symbol period, can you figure out if it's early or late? Okay. You want?
The distance between them should be in such a way that we can make sure that there are no more than 2 clock transitions within the period.
Okay.
Then we will be able to flip flop.
Okay, so how many do you need? 2. So first of all, I think it looks like if you sample it only once in every symbol period, it's not very easy to tell. Okay, you will simply get the data and nothing else. Okay, so if you sample twice per symbol period, so I mean this is again contrived. I'm sort of leading you to the answer, but at least you can think about it. So when I say twice per symbol period, that means that you sample on the rising edge as well as the falling edge. Okay. So then will you be able to tell? So let's say the clock falling edge is here. Okay. Okay. This is the falling edge. So how would you figure out what is the difference between this and if the clock is the clock late or early now? Huh? It's early. It is before the transition. Okay. So this is early. So what happens if it is late? Okay, so how do you distinguish between the two? So let's say I have, for instance, I can have the opposite of this. Okay. Then also I am sampling these values. So how do I distinguish between the two cases? Huh? Not? Okay, whatever. You use how many ever you want. How will you tell? Okay. But you don't know where the transition is. You just have a number of samples, right? Right, you sample with the rising edge or the falling edge. My eventual goal is to tell whether the falling edge is before the data transition or after the data transition. So which samples do you take? So I think people have been saying that you need 3 samples, not 2. Now the 3 samples can be like all from successive rising edges, successive falling edges, or 2 from a falling edge, 1 from a rising edge, various combinations, right? So which one? 2 rising and 1 falling. Okay.
So if you have a 0, 0, 1, means that if 0, 1, 1, then it is 0.
So you want to align the negative edge with the transition. Okay. So you take the samples of the previous positive edge and the following positive edge. Okay. So you have a negative edge on either side, you have rising edges. So you take the samples at the falling edge and the rising edge before it and the rising edge after it. From that you will be able to tell. Okay. So let's say this is the data and this is the falling edge sample. You also look at the sample at the rising edge before that and the rising edge after that. Okay. So if it is the same as the rising edge before that, then it is early. Now, if this is from the falling edge, if the sample value is the same as the rising edge from the following rising edge, then it is too late. Okay. You sample it half period away, both ways. Okay. You want the falling edge to be aligned with the transition. So you look at half period earlier and half period later and see if the sample values are the same. Is this okay? Yeah. Yeah, let's see what happens. Both of them will be same as the center one. No, that's not the case, right? First of all, what happens when there is no transition? All will be same. So all will be 1 or 0. That you have to ignore. Okay? Because when you have no transition, you can't do anything to detect the phase. Now if you do have a transition and if it is aligned, exactly what happens? So this goes to a flip flop, right? So it will not give you 0, it will give you either 1 or -1. Now if there will be some noise and it will steer it to 1 half the time and 0 remaining half the time. Okay. So on average it will become, the contributions because of this will be will be non-existent. Okay. So you look at samples at half period before and after. So if it is the same as half period before, then it is too early. If it is same as half period afterwards, it is too late. You also know that the one half period before and one half period after will be different. Okay. I mean, if they are not different, then you can't do phase detection, so you ignore that anyway. Okay. How many flip-flops do you need? How many flip-flops? 2. 2, 3, 4.
Because if we have compared the current sample to the previous and the next.
Okay.
We have to go further.
You have to?
We have to have all the systems.
Okay.
We need to memory.
So 2, 3, 4. What is the answer?
2 flip-flops to generate the 2 products.
Okay, let's see. What is the scheme? You have to have 2 samples at the rising edge and 1 at the falling edge. Okay. So basically, you need 3 flip-flops, right? You need a little bit more, but that we will see. So this 2 will give you the samples at the rising edge. This will give you the sample at the falling edge. Also, the 2 samples at the rising edge should be 1 period apart. Okay, they are not the same thing. So essentially, you pass the delayed data to the second flip-flop. Okay. This is the data and this is the clock. Okay. Now, we usually call this these samples A, T and B. Okay. T stands for the transition sample and A and B are the data samples. That is when the clock and data recovery circuit works properly and everything is in alignment, T will correspond to the transition sample. And which is earlier, which is later? A is the older data than B, right? Let's say we again go to an up-down, a charge pump with up-down inputs. So we either raise the up or raise the down or have both of them at 0 if we don't want any movement in the phase of the VCO. Okay. So we have 3 inputs, the transition sample A and B. So we have to find out how to relate the up and down to these things. What do you do when A, T and B are all 0? Nothing. So that means that there is no transition in the data. So both up and down are 0. What about 1, 1, 1? Again the same thing. There is no transition in data. What if A, T and B are 0, 0, 1? 0, 0, 1 is early. Okay. So what do you do? So up and down. Up or both will be 0. How do you decide that? Yeah. So basically, if you want to make the VCO delay, if you want to delay the output phase of the VCO, you have to reduce its frequency. Then the edges will start getting delayed, and then it will reacquire alignment depending on the bandwidth of the VCO. Okay. Similarly, if you want to advance the phase of the VCO, you have to increase its frequency. So the successive edges will come closer and closer together. Finally, it will lock to the right thing. So in this case, if it is too early, you have to delay it. So down is 1, up is 0. And 1, 1, 0 is the same as 0, 0, 1. Okay. The exact polarity of the data doesn't matter to us. What do you do with 0, 1, 0? Huh? It cannot occur, so we'll leave it as again 0, 0 or something. Let's see what to do with that. Okay. What about 0, 1, 1? It's the opposite case, so you have to do this. Now, the 0, 1, 0 and 1, 0, 1 should not occur really, because the data is transitioning from one symbol to the other. So, you can't have it that the symbols at the two ends are the same, but in the middle you have a different value. But because of noise, etc., and maybe limited eye opening in the data, it can happen. So, you can get this. So, you can either leave it or don't care, but typically what you do is you just push it to one side. Okay. You just push the VCO to one side. So, let's say you just make up and up equal to 0 and down equal to 1. Okay. It will just steer the VCO to one definite side instead of just hanging there. So, it turns out to be better in practice than leaving it at 0. Okay. And how do you realize this truth table? Is there some way to simplify this? Like, huh? Anyway, you can realize this exactly. There is no problem. Okay, you just need a combinational logic with 3 inputs and what's that? AX or T. Which is AX or T? Up is AX or T. That is if you choose to make this X 1. Okay. And down is? Down is what? This. Is it? Both the don't cases will become 1, 1. Okay. So that may be okay in practice. So what happens is if you do it with this, you realize it with only 2 gates. I mean, it's a simpler realization, but you can realize the whole thing. That's not a big issue. If you are working at extremely high speeds and you want to simplify the circuit implementation as far as possible, you can simplify the truth table a little bit like this. Okay. And also note that if both up and down are 1, then it's not contributing to the phase advancement or receding of the VCO. Okay. Can we take these A, T and B and feed them to these logic gates? Delay where? Which has to be delayed? B has to be delayed by half. Yeah, actually what you want to do is just see, the problem is A and B are aligned, meaning in their transitions. A and B are one symbol apart, whereas the transitions of T occur half a symbol apart. So you need to delay T by half a cycle. You don't need to delay B at all, right? So what do you do? So again, we are talking about high speed, so if you want to economize the implementation as much as possible, you don't use a full flip-flop, you just use a latch. Okay. If you use you can use a positive edge triggered flip-flop. What happens is then you will have positive latch, negative latch, positive latch, negative latch, negative latch, positive latch. So effectively you are combining these two to get a single latch. That's all. I think we did this once before when we did deserializers or something. Okay. So now A, T and B give you pulses which are aligned in time, and the output, what will the output be? Output of the XOR gates. So let's say this is the combinational logic, and this gives you up and down. Either up and down will be one period wide pulses. Okay, the pulse width is always one period. That's why it's a digital phase detector. It either gives you 1 or 0. Okay. So either up is 1 and down is 0, or up is 0 and down is 1. So, but the width of up and down don't change. So it's not like the average value is proportional to the phase of something. It only gives you an indication of whether the phase is before or after. Okay. Yeah. Yeah. So basically, the output of the phase detector is persistent for one symbol period. Okay. After that, you get the output of the next transition. So corresponding to each transition, there is a phase measurement. That phase measurement lasts for one symbol period. So during the next symbol period, you get the phase measurement corresponding to the following transition. If there is no transition, you will get 0. That is no information. If there is a transition, it gives you up or down depending on what the phase difference between clock and data was. Okay. So this is known as the binary phase detector or bang-bang phase detector. The term bang-bang comes from bang-bang control. Okay, if you have a binary digital control system, sometimes you do that, right? If something is too much, you just turn it off, and when it's too little, you turn it on, whatever that it is. Okay, so that's known as bang-bang control. So that's what this will be. Okay, this will just step the VCO to a higher frequency or lower frequency, depending on if the phase is retarded or advanced compared to the data phase. Okay. And it's also called Alexander phase detector because of the inventor's name. Five by? No, okay, this is a binary phase detector, so you can't define the gain, right? And it's like, what is the gain of a comparator? It is infinity at the zero crossing. So it's exactly the analog between, let's say you have a linear amplifier and a comparator, you have a linear phase detector and a binary phase detector. Okay. Two samples per bit. This is 2 samples per bit. Okay. What do you want to do? So first of all, you are saying you compare these two, okay? And if you are like if it is the same, like you can't say, right? Also, if there is no transition, if you have one here and one here, it still tells you to do the same thing as this. Okay. So here, maybe this is the falling edge, and it is too early. I mean, in this case, the clock is too early. In this case, if you don't have any information, even then, it will tell you that it is too early, right? Is that okay? How? You have to implement a circuit to do it, right? And this is that circuit. Take 2 samples? No, you can't, right? Because yeah, so the analysis of this is more difficult and we won't do it, but we'll analyze some aspects of it, but analyzing the dynamics of that is more difficult. Just like analyzing the dynamics of, if you have an analog loop with a quantizer inside, that's a hard nonlinearity, okay? Just like you are familiar with delta sigma modulators, right? So you make some approximations in analyzing that. So some similar things can be done here. We'll analyze some essential parts of it. In this case, what is most essential to us is the jitter, okay? So you can imagine, when you have a digital control system, it will always oscillate, right? You can think of it as always being in unstable condition. Meaning, when you have any quantization, the desired output, the input may not be equal to either one of the quantized levels. So it will always bounce between two quantized levels at least. That's the property of a digital control loop, isn't it? That's known as limit cycle oscillation. Not necessarily limit cycle oscillation, but yeah, something like that. So here also what happens is it is never stable. The output of the phase detector will always oscillate between plus and minus 1. Okay, we have to see what the effect of that is. Okay, what do you want to do with that? 2 samples in, are you talking about 2 samples per period or 4 samples per period? 4 samples. Yeah, you can do it. It's just that, if you have more samples, then first of all, you may not, you can do clock and data recoveries in logically very easy ways, but it's hard to take all those samples. Okay. So let's say you are operating at 10 gigabits per second, then you are talking about samples separated by 25 picoseconds. Okay. It's hard enough to do 100 picoseconds. Now if you oversample it, all these things become easier. Okay. So you will essentially have a digital or sampled representation of the signal, and you can do a lot of logical things. You can store it and do all those things. But you would like to do it with the minimum rate possible. Okay. Yeah, definitely. If you have a lot more samples, then you can do more things. That's true. So let's say we have a binary phase detector, and then we go to the charge form that we always had. Okay. And we have this loop filter. And the VCO. Okay. So what happens to this voltage? What will that waveform look like in steady state? So what happens is the charge pump will put out either plus ICP or minus ICP into the loop filter. What will that do to this voltage? Huh? No, it will not be triangular. See, the part across the resistor will be a square wave. The part across the capacitor will be a triangular wave. But the amplitude of the triangular wave is much, much smaller than the amplitude of the square wave. Okay. So that is again another meaning of this R times C. The 0 is at a frequency much lower than the reference frequency or the input frequency, right? So another way of saying that is the voltage across the capacitor is much smaller than that of the resistor. So this is approximately a square wave. What is the amplitude of the square wave? So this will be plus minus ICPR. Okay. What is the effect of this on the VCO? So let's say there is a transition in every, the transition density is 1. Okay. That is, you have alternating data. Now CDR analysis is further complicated by the random input data. Okay. So for this purpose, let's assume that the input data is 1010 pattern. So what happens to the VCO phase? Yeah, first of all, its average frequency will equal that of the input. Okay. That's why the phase detector gives you 0 on average. That is, in some periods it will give you 1, in some periods it will give you minus 1. Okay. So what will happen to the edges of the clock? Yeah. So one period it will be early, next period it will be late. And how much will that be? So essentially you will get from the VCO you will get waveforms of this type, right? one is a long cycle, the other is a short cycle. This is a highly exaggerated picture, but you get the idea. So, what is the phase difference between in the two cases? So, if in the eye diagram, if you plot the eye diagram of the clock and the eye diagram of the data, so let's say the data is perfectly rectangular, so the eye diagram will look like this, okay, this is the transition. The eye diagram of the clock, you will see two edges, one here and one here, one before the transition, one after the transition. What is the spacing between the two? How do you calculate that? It jumps between two phases. How do you calculate the phase difference between the? Okay. And what is the width of the pulse? Yeah, what is it? It's the data rate. I mean, it's the data period. Okay. So, the jump is 2 ICPR. Right. So, times 2 pi kVco, integral of this with respect to time from 0 to t. Now, this t, note that the worst case is not for 1010 pattern. The t is really small for a 1010 pattern. It's the minimum possible. It's one symbol period. So, what happens if you have consecutive identical digits? This will be some t times n, where n is the number of consecutive identical digits. Then the phase will drift a lot more. So, again you will have a limitation with respect to the CID. Okay. So, you have to figure that out, what an acceptable variation in phase is and what the maximum n is, where the phase doesn't run away for a long time. Okay. So, if you just have 1010 data, this is just t. Okay. So, anyway, whatever it is, this integral is very simple to evaluate. So, this is 4 pi ICPR kVco times n times t. Okay. So, that is the jitter. I mean, this will be there even in the ideal case. If the data has no jitter, the VCO has no noise, no other components have noise, simply because of the digital action of the control loop, you will have this jitter. Okay. So, when is the maximum number of identical digits that you expect? This is what happens. Okay. So, you will have to limit the value of ICPR times kVco. This is what you have control over, right? This t is the data rate, it is a fixed number, and n is also the characteristics of the data. Rather, maybe n is also, you have some freedom over sometimes. But ICP times R times kVco are the design parameters of the loop. So, this is known as the bang jitter. Okay. And this is the peak to peak value. Huh? Why? No, you don't. Right? You have it only for one period. It's not related to the consecutive identical digits, right? Yeah. Yeah, that's what. But when there are no transitions, you don't have anything. Meaning, the Hawk phase detector gives you a 0 average, right? Whereas this gives you a plus minus 1. So, it is somewhat similar. There also you will have jitter. I agree with that. No, it will be less. But isn't it more here? See, if you don't have consecutive identical digits, what happens in a Hawk detector? Up is 0 and down is 0. Okay. What happens here? Here also both are 0, but the VCO is oscillating at a different frequency. Right? Yeah, so what, I don't know if we can discuss it today, but see, the advantage of this is in the Hawk detector there was a phase offset because of the clock to Q delay of the first flip-flop. Whereas in this case, it is true that there is a deterministic amount of jitter, but there is no offset because the characteristics are like this. It has supposedly high gain at the 0 point. There is no static phase offset in the bang-bang detector. That is the biggest advantage of the bang-bang detector. That's why this has become more popular. It was not used, linear detectors were used, but as you go to higher and higher frequencies, the delays in the flip-flops and so on become a significant fraction of the clock period, the data period. So the offset also was increasing. So the contribution because of that non-ideality may be even more than that because of this much. Okay, this is something that you can control and limit. But there is no static phase offset. That's the advantage of the bang-bang detector. Because the clock to Q delays here don't affect anything, right? I mean, it's just going to a logic level. Like they all go through the same clock to Q delay and doesn't have any effect on the output. Okay. Yeah, this is somewhat incomplete. That's why I'll take a couple of more classes to wrap this up and also wrap up the course. Since we'll just stick to the presentation schedule and start from tomorrow. But I think this information is enough to do the assignment, like design the bang-bang detector and do the assignment. Okay.